Hi guys, today we're going to solve a sample problem in Chapter 4 of Thermodynamics and Heat Transfer. The first law of thermodynamics. The sample problem is a piston cylinder device initially contains zero point 0.8 cubic meter of saturated water vapor at 250 kilopascals. At this state, the piston is resting on a set of stops, and the mass of the piston is such that a pressure of 300 kilopascals is required to move it. Heat is now slowly transferred to the steam until the volume doubles. Determine the final temperature, the work done during this process, and the total heat transfer. The given values are volume is equals to zero point 0.8 cubic meter, the pressure at saturated vapor at 250 kilopascals, and another pressure is equals to 300 kilopascals. We need to apply the first law of energy balance to the system to determine the temperature. We use the formula energy at initial state added to heat input subtracted from work output equals to energy at final state. We have the assumption kinetic and potential energy is equals to zero because our cylinder is stationary. So our equation now is internal energy is equals to mass multiplied to the difference of internal energy by mass basis at state 3 and the internal energy by mass basis at state 2 added to work output is equals to heat input. From table A-5 of our property table, for saturated vapor at 250 kilopascals, we have specific volume at saturated vapor equals to 0.71873 cubic meter per kilogram and internal energy at saturated vapor equals to 2,536.8 kilojoules per kilogram. In determining the mass of the vapor, we use the formula mass equals to volume over specific volume at state 1. Then plug in the values. We have 0.8 cubic meter over 0.71873 cubic meter per kilogram. Cancel out the same units. We have 1.113 kilogram. So we know that at the final state, the volume doubles. Therefore, the specific volume at this state is specific volume at final state equals to volume at state 3 over mass. Then plug in the values. We have 2 multiplied to 0.8 cubic meter over 1.113 kilogram is equals to 1.436 cubic meter per kilogram as our specific volume at state 3. From the superheated tables in table A-6 in our property table, the pressure at state 3 is equals to 300 kilopascals and the specific velocity at state 3 is equals to 1.4375 cubic meter per kilogram. We can interpolate to find the temperature and internal energy at state 3. For interpolation, we use the formula specific volume at saturated vapor at top minus specific volume at saturated vapor at bottom over specific volume at saturated vapor at top minus the specific volume at saturated vapor at mid equals to temperature at top minus temperature at bottom over temperature at top minus the temperature at mid. Plug in the values. We have 1.34139 cubic meter per kilogram minus 1.49580 cubic meter per kilogram over 1.34139 cubic meter per kilogram minus 1.4375 cubic meter per kilogram. Then cancel out the units. We have equals to our temperature 600 degrees Celsius minus 700 degrees Celsius over 600 degrees Celsius minus the temperature at state 3. So our temperature at state 3 is equals to 662.24 degrees Celsius. We also use interpolation in finding the value of our internal energy at state 3, in which it equals to 3,398.47 kilojoules per kilogram. In determining the work done during the process, we need only to be calculate between state 2 and 3. Since there is no change in volume between 1 and 2, so we use the formula work output is equals to pressure D volume integrated from state 2 to 3. Then arranging the equation, we have pressure multiplied to the difference between volume at state 3 and volume at state 2. Plug in the values, we have 300 kilopascals multiplied to 1.6 cubic meter minus 0.8 cubic meter multiplied to 1 kilojoules over 1 kilopascals cubic meter to convert the units. So crush out the same units, so we have 240 kilojoules as our work output. Next, the heat transfer can be determined from our first law balance. It expressed as heat input equals mass multiplied to the difference between internal energy at state 3 and state 1 added to work output. Plug in the values, we have 1.113 kilogram times 3,412.3 kilojoules per kilogram minus 2,536.8 kilojoules per kilogram is added to 240 kilojoules per kilogram. Then cancel out the same units, so we have 1,213 kilojoules per kilogram as our total heat transfer. So that's all for today's video. I hope you've learned something and see you in my next video.